Can you hear me? Yeah? Oh, okay. The seats in front here and in the middle. So. Okay, I think we should go ahead and start. Brian, is this is fine? Okay, great. So welcome you all for this very exclusive conference called International Conference on Computational Photography. And this is the tiny workshop for this small conference. Okay, so today we're going to have 4 talks, and all of you have seen the program, I hope. And I just want to ask a few questions. So, did you guys have any problem getting here, so that we can improve the signage or something? Did you have any problem in the wireless, for example? Everybody's fine. Okay, so one thing I want to mention in terms of wireless is that you have the account and password, but when you log in, it says which department you are in. So you just say undergraduates, and you're fine. So you say continue, and then you're fine. Okay? Okay, so I think without further ado, I'll pass it on to Hendrik, and he'll introduce the first 2 speakers. Okay.
Thank you. So welcome from my side. So I'm one of the co-chairs of this conferences, and I'm extremely happy to introduce Kari Pulli, who will talk about the FCam, the Frankencamera. Kari Pulli received his PhD from University of Washington, and then was a researcher also at Stanford University before he joined Nokia, where he worked at a couple of different places, both in Finland as well in the US. And just very recently, he actually switched to NVIDIA. So I'm looking forward to your talk.
Thank you.
So hello, this is working actually?
This is only for
for remote, okay, fine. So yeah, that's, I haven't had time to update the slides. I started at my new job this Monday, so I at least used one slide with the new template, but all the work was done while I was at Nokia. So the rest of the slides are with this template. So computational photography is the topic of the conference. I kind of first wanted to give my definition or like contrast it to the mobile, which is the topic. So the idea is to overcome limitations of traditional cameras. Often you do it by taking several images with different parameters and then combining the images and get hopefully better images out. Mostly the work has been done in the labs using, by researchers, by professionals, and the camera often is on a tripod. The situation is very controlled. And people use high-end cameras that have very nice optics and sensors that give high-quality images. And then the images are later processed on a PC to create the images. To output images. In mobile computational photography, the idea is to bring all these techniques out to the real world, and that in practice means camera phones, because that's what everybody carries, or most people carry. And but the camera phones, they give new challenges. The sensors are much smaller. That means they are also noisier. Optics is smaller as well. And the devices are handheld. Not too many people carry tripods with them that match their cell phones. And then we'd like to make it online so that the processing happens immediately or right after taking the images, so that you can enjoy the results, you can check whether you got the right results, whether you have to retake the images, and then maybe you can share them right away, like post them in your Facebook page or something. Here's a slide kind of showing, contrasting camera phones versus traditional phones, traditional cameras. And the numbers kind of show that if you want to have a big impact to everybody, then that's the place to be. So the same a little bit in numbers. So in 2003, there were 85 million camera phones that shipped. And last year, over 800 million camera phones were shipping. And that's 2 phones out of 3 that had a camera. Going forward, there's going to be 1.3 billion. Most of the cell phones having a camera. And the average resolution is growing. The couple of years ago, it was 1 megapixels, then 2 megapixels. And already last year, over 100 million phones with at least 5 megapixel. And then average going there. And that year, there would be over 500 million camera phones with 5 megapixel camera. So it's not just toy cameras anymore. But when you start doing computational photography on a camera phone, there are some problems. One is lack of access to the camera, lack of precise control. Usually the cameras, they need to have, for normal photography applications, these control loops that are running there, doing their like the 3A algorithms, autofocus, auto exposure, auto white balance. But if you can't stop those control loops, then that's a problem, because then you can't control the settings as you want. And then also, even if you can stop them, typically the things that you can tell the camera do are limited. They are enough to write a point and shoot application, but not necessarily enough to make good computational photography applications. But this is fairly easy to change if the manufacturers want to change that. And this is changing already. However, there's a second problem, which is that most people, even the ones that implement the APIs and design them, have kind of wrong mental model of a camera. They think that camera is a monolithic thing that has a single global state, and that's not correct. Cameras are pipelines, and this is like the image sensor already is a pipeline. There's at least 3 stages typically that are happening at the same time. So while you're taking an exposure, the next image is being prepared, and the previous image is being read out. So all of those things happen at the same time. And then as the images go out, they go to an image signal processor, which also has several stages. Now this has a couple of implications, or a couple of choices that you can do. One is that you can actually run it as a pipeline, and then you have many images in flight at the same time, and that's kind of the efficient way of using your resources. The other one gives you more control, like just set the parameters. That actually is the model that's kind of encompassed with this global state. Set the parameters, take an image, wait until it's out, redo it. But that takes lots of time, increases latency. And really the thing where you can shoot yourself in the leg is that if you kind of think you have this model, but you actually have this model, then you think that you can change the settings, and in your application program you change them atomically. You think everything is good, but you may change the settings at different parts of the pipeline. They actually affect different images, and then you don't even know what you're getting. So that's a no-no. So this kind of simple illustration why this latency is bad. So often you take a bracket bursts, image bursts, and here's an exposure burst, first, second, third. Yeah, I mean if you take too much time, things happen that you might not be able to handle. So garbage in, garbage out. That's kind of concrete example why those state changes need to happen fast. FCam, short for Frankencamera, a joint work with mostly with Stanford and Nokia. It's kind of tries to be an answer to these problems. It's an architecture for computational cameras that makes the camera programming easy and still exposes to the programmer maximum capabilities of the underlying hardware. So this kind of system diagram, we have the application processor, the CPU here. It sends requests to the sensor. There's the image processor, and we have additional devices. And there's like images, statistics, and metadata go back to the CPU. The first part is the sensor here, and as we described earlier, it is a pipeline, and it converts these shots into images. So there's no global state. Instead, the state is in these requests, in these shots, and all different stages might have different state because the state travels in the pipeline with the request. Then we have the image signal processor. The most important task for it to do is to get out of the way. So if we want the raw image data, we would like to have that, and well, that's what ISP does, converts the raw images to JPEG and so forth. So if we want to do all of the processing ourselves, we want to just bypass the data. Another important thing that we want from it is the statistics. We could compute, if we just get the image back to the CPU, we could compute the statistics ourselves, but it's often cheaper to do it here. And with the statistics, we can do, like with histograms, we can do our own auto exposure and auto white balance. With the sharpness map, we can do our own autofocus routine. It just makes it easier and faster if we have those available. Then there are the devices. Some typical devices are a lens or a flash, and they are controlled by actions that are triggered to happen during the exposure. So these actions also are synchronization mechanism. You can synchronize other things like reading other sensor information like gyros, or have other devices to go off at the same time. And afterwards, when the image data and metadata comes back, the devices add their own metadata to the frames. So in summary, it's the idea is to give full control to the programmer of all of the settings without any daemon messing things up under you.
Kari?
Yes?
Where does the viewfinder fit into this picture?
Viewfinder is here, and you don't see the well, display is not, but it's just that typically viewfinder has lower resolution, and therefore this can run faster. So there's no like big conceptual difference between viewfinder or any other, whether you take still images or bursts or video. I have some examples later. There's currently two implementations. There's the Frankencamera version 2. This big monster that takes Canon lenses. Unfortunately, it only has cell phone size sensor there, so it's the lenses and the sensor is not a very good match, but the version 3 will fix that. Then there's the Nokia N900 Linux-based smartphone that runs FCam and has been used by lots of universities in their teaching of computational photography and related things. Inside, those implementations are fairly similar. Both are based on OMAP 3430, which is basically a whole computer in one chip, system on chip. And it has the compute elements and lots of peripherals, and then there are the sensors and lenses. This diagram kind of gives idea how the system actually works. So I'm gonna make you dizzy running this quickly through. So here's the FCam software part. Here's some system kind of driver levels, Linux kernel, and here's the hardware. So the requests for shots come from your application. They come to this sensor object, and we have three threads running there. One is the setter that kind of sets everything. This one handles the returning data, and this one takes care of the actions that need to happen during the exposure. So the requests come to the request queue, they go to the setter, the setter figures out which actions need to go and sets up the action priority queue. It also sends the parameters to the driver, camera driver, and updates the shadow queue that, okay, we have asked this kind of images, please match them when they come back with the requests. And then when it's when the queues kind of get to the position, well, then the image is being taken, data comes back. At the same time as image is being taken, the actions are triggered, so lens settings, flash, and whatever else you might have. And then the requested state is matched with the data that comes back. The metadata is added, the output frame queue is updated, and the frames come back. This is all implemented in an open source project. There's a website, fcam.garage.mimo.org, where you can download source code for the N900 implementation of FCam. There's instructions how to get started. There's extensive documentation. There's examples. Here's an example of the documentation, so done with Oxygen. Okay. Now moving on to some applications. So this is, HDR imaging is the prototypical computational photography application, so let's start from that. Traditionally, you take several images with different exposure times, and then you generate this image that has kind of higher dynamic range that you can fit into 8 bits per pixel, so that tries to estimate the actual irradiance in the environment, and you need to calibrate your camera to actually tease that the data out of the input. And this is kind of the science part. But you can't display this except something like this. So with normal displays, you have to tone map it back down to low dynamic range images. And this is the art. Well, kind of science and art. So there's so many different algorithms, and those algorithms have so many different knobs that you can have hundreds of different ways of tone mapping it back. So that's where your kind of artistic opinions come into account. There's a way to bypass this bigger loop. So the idea with exposure fusion is to let's take those 3 images and then figure out that, oh, here the foreground data is good. Maybe I should mostly take the pixels of the foreground from here, and that's noted by this weight map here, and the sky is nice over here, so let's take mostly the sky from there and all the rest from the center. But if we just blend those images together with these weights, we get visible seams, so that's no good. We can do a multi-resolution blending which hides those artifacts, and we use Gaussian pyramids and Laplacian pyramids. So take the next coarser level of the Gaussian, upsample it, it's a blurred version, take the difference. So now adding these together gives you the original, and then you repeat that. So this is called Laplacian pyramid. So ideally you go all the way to 1 pixel, which is the average of the image, and then add the details back. And we can do this kind of processing here. So here's the input images, there's the Laplacian pyramid, there's the Gaussian pyramid of the weights. So at the corresponding levels of resolution, we multiply the details with the weights, and then we sum them all up to get this fused pyramid, and then we reconstruct the original image from that. And we have implemented this on N900. And here's the metering part is first that we take kind of bursts of 2 images, analyze whether they are too dark or too bright or something. We just have to have, in the dark image, we need to have some fraction of bright pixels and vice versa. And that's how we do the metering, to figure out the parameters to use. But the user is not shown this sequence of like flickering images. The user is shown one image that merges those 2. If you have only 2 images, you can simply average, and it gives a good result. You see details here and there, here would be the kind of corresponding exposure, which loses the details both in the bright and dark areas. And a little bit FCam code. So we can create these vectors or shots. We create 2 of them. We set the exposure parameters, and then we have a loop where we tell the sensor to stream with these parameters. Then we get back 2 frames, and then we analyze the metadata, in this case histogram and the previous exposure. This is our own magic function that calculates the next exposure that we should have, the same for the long exposure. And now we would do the viewfinder part here that Michael asked. So we do our blending, and we just call display routine and pipe that. So we want to do the viewfinding mostly under our program control as well. It makes it a little bit slower than if you would use kind of fast path in hardware. And here's the output, so 3 input images. All of them are bad in some way. And the output image that gives enough detail, yes.
Given that you have complete control of the camera, you can calibrate it, you know all the hardware, why not do the full HDR pipeline? Always going to be too slow?
One reason is that if you want to ship this with all the devices, they have all different sensors, and then you have to repeat that calibration. That's one answer. So this is kind of much more robust way of doing that. Another answer could be that this is faster to process. The cell phones are kind of compute limited still. Yes.
Are these frames captured at 30 frames per second? Is there any reason you can't go faster?
Well, there's internal bandwidth, there's processing limitations. The viewfinder, do I have?
I was just wondering how fast the frames can be captured.
This 5 megapixel images, in practice, I think we can take those 5 megapixel images under 1 second, all 3. The sensor itself probably could do like 10, 15 frames per second, but that's just a sensor. It's not guaranteed. The ISP can't even stay with that speed. And there's not enough internal bandwidth, and there's definitely not enough compute power to process those images. Okay, so this kind of the code. Very similar as before. Declare sensor, declare a burst of shots, set the parameters, set also what kind of, like we want the raw image or maximum image size. Now capture this burst and get frames and display.
Question.
Yep.
What would be the effect of motion in there when you combine those images?
Well, that's a long answer. I'll actually defer the answer to this example partially. Well, one thing is that you have to register the input images for sure. So that takes care of the, at least partially takes care of the handshake. Then if your targets move, I would say that the short answer is that you choose one of the images, which the baseline that freezes the time, and then you add as much information from the other images as you can so that the data is still consistent. Otherwise, you get some kind of blurring or ghosting artifacts. But I'll address that a little bit with this application. Yes?
One of the frames as a key frame and register the remaining to it?
Exactly. That's kind of what I was trying to say. So low light imaging. So I mentioned that's a problem with small cameras. So if there's not enough photons for your optics and sensor, then you can increase the sensitivity, the gain, and you get noisier output, or you can increase the exposure time then you get blur because you get handshake and maybe object motion. And our solution is we'll just take 2 images and kind of try to use the best parts of the 2 images. So this is the camera motion in time. If we take a short exposure, there's not much time to move. We get a darker image. It's noisy. The colors are not very good. the long exposure gives good colors, enough light, but it's blurry. So here's one of the inputs. This is the noisy input. There's the blurry input, but if you combine, we can get some nice output. So the first part is always the registration. I'm skipping that part. Then what we do next is we calibrate, we kind of boost up the colors here so that they roughly match the colors here. And then we fuse the images so that it tries to be sharp in appropriate places and smooth in appropriate places. So first we have the two inputs, and they are registered. So we know, for example, this pixel, that pixel corresponds for that. Using that data, we can calculate these calibration curves that, let's say, 30 corresponds to 170 in green channel on the average, give or take. And now we can boost this image into that image. But if we look into details, it's quite noisy. Then next we want to fuse the images. We process luminance and colors separately. Here's the intensity fusion. There's the short exposure is this noisy red signal. Ideally this is step edge, and then the long exposure blurs the step edge. And we want to kind of weight up the data close to the edges. How do we find it? We look at the difference signal. This is likely to be edge. Now we give a higher weight to the short exposure. Elsewhere we give a higher weight to the long exposure. And again, we do multi-resolution way of combining this, in this case, wavelets. This just shows the kind of, here's a noisy image and a little bit blurry image, and you get a higher signal-to-noise ratio after this kind of combination. If we increase the blur, we still get quite good output. So there's a fairly noisy and very blurry image, and then the output is still okay. The colors we mostly take from the bright image because the colors are better. You can, if you look here, it actually is blue, where it says gray here, and the reds are much deeper here. So, for example, in these areas, we take the information from here. That means the high weight. And the lower weight here is that where, for example, here it's saturated, so we want to get the data over there. And here's short and long result and detailed, so noisy, blurry, better. And this kind of addresses the motion, in this case object motion. So these women didn't have time to move too much during this exposure, but did have time to move during that exposure. Our method actually handles that fairly well because in this case the luminance mostly comes from here. And even if we take the chrominance from here, you can hardly see that. Then we have a, which I don't have time to go through, we have a newer result that actually analyzes when this happens, and in this case takes also the color information from there so that you won't get the color blurring. Final example from outside of the lab. And detail.
Question?
Yes?
If you do like this function, user is sort of responsible taking two different...
No, user presses on the button only once, and then the system takes two images and does the processing automatically. So it looks like fairly regular camera application, just pressing.
Would it be possible to do this in video?
Yeah.
Sure.
Yes. Yeah. I mean, there are other artifacts. Then, like if you then have the long exposure to be too long, you're gonna get jumpy video. If you just then make it too short, then you don't gather enough photons. But in principle, I suppose you could try to apply it in video. You could also, what you could do with video is that if you have kind of short image exposures, you can just align consecutive frames and try to get rid of the noise that way by averaging. Okay, another burst application is all-focus imaging. So here are 3 input images. One is focused in the foreground, this one at the center, this one in the background. And we want to get this kind of image that is focused everywhere. And the focus of this work was to figure out which images to take, not the combination. So traditional passive autofocus works roughly like this, so that you just run through different settings and analyze where it's sharpest, and then you take one image which is the sharpest. In our case, it depends more what kind of the scene is. If scene has objects at different depths, you have to take many images. But if we have this kind of scene that has only a thin concentration of objects at particular depth, then in this case maybe one image would be enough. And we want to minimize the number of images so that the capture is faster, there's less sensitivity to motion, and then the processing is faster too. And here's a video that shows the system live. First, you see, we still need to do this lens sweep, and it's okay. That was too fast. Let's do it slower. These rectangles kind of indicate which areas are in focus, and then we collect that information, and then we can analyze that we have 3 groups of different depths. Then we take 3 different exposures with 3 settings: near image, middle. And actually that's one of the nice things using the N900 versus the bigger camera, is that the lens moves really fast. So even though we needed to move the lens between the exposures, we can capture those 3 images in about 1 second. Okay. Yes?
What happens if the depths overlap? Are you getting edge artifacts?
Well, that depends how you process the images. We use an open source package how to merge the images. But yeah, if you have a receding disk like we actually had there, well, if it doesn't have patterns, then there's no problem. If it has patterns, then that can create a problem. For example, you need to maybe take dense set of images. And it depends how good your merging algorithm afterwards is, whether you see emerging artifacts or not. Okay, so a couple of additional applications that we had on the SIGGRAPH paper from last year. This was HDR Panorama. We just cycled between taking as the user rotates the camera, then taking a bright and dark shot. In practice, we created 2 panoramas, registered those together, and then merged them into a single panorama where you now can see the details both in the sky and in the grass, because in the input it was either or. Here's a different approach for taking images with not enough light. So if you had the tripod and nothing moves, you're good. If you don't have that, you can just try to hold it very still. You usually will fail, but you do that often enough, you maybe get lucky once. And rather than doing this repeatedly, we tried to automate that, added a gyro and then just analyze the gyro output to see that, okay, now it was fairly steady, let's keep this one. And this application showed, yes?
There are multiple images being captured, or there's an image being captured when the gyro?
The sensor is capturing all the time, but if the gyro says that it's no good, we don't further process it at all. It's just dropped on the floor immediately. Only if the gyro data says it's good, then we do the rest of the processing and save and show. Yes?
Is it gyro or accelerometer?
Gyro. This device has both. Accelerometer is not good enough. Rotation, and most of the handshake comes from rotation. Think about it, if you move camera laterally, and how much you have to move, if your object is, let's say, 3 meters away, how much you have to move that you make 1 pixel error? It's like this big motion. So, gyro.
What's the downside of just analyzing the image and dumping it?
You could do that. If you have more processing power, this is kind of like, well, the assumption is kind of that it's much cheaper to process the gyro output. If you don't have gyro, you could just, if you have enough bandwidth and you can store, you would just stream all of the images, process them later, keep the best one. You could do it.
The focus you do there, is that on the sensor or is it the lens moving? Or?
Lens is moving.
How fast is that?
Eddie, do you remember?
The lens can go from one end to the other like in 100 milliseconds or something like that. Or it's certainly under a second. It's very fast.
Yeah, it certainly goes under a second from like the closest to farthest. But yeah, it's fast, but I don't remember the speed. Okay, this was this example showed that one of the flashes was strobing, and then towards the exposure, the other flash was then giving much stronger second current flash that kind of freezes the cards where they are. There is NSF gave a grant to popularize FCam or use FCam in education in U.S. universities. The PIs are from Stanford, Mark Levoy and Mark Horowitz, from MIT, Fred Durand, and Bill Freeman. The idea is to provide computational photography courseware, which includes the hardware, the version F3 of the Frankencamera, and N900s. I used to kind of be the contact, but as I'm not there anymore, Timo Ahonen is now the guy to contact to get these as loans. And if you're not in the US and you want to get these, it should be possible also, but you have to pay for it, and I think it's going to be in the order of 10K US dollars, which is hardly anything in euros. So. This is the current F2 camera. That's an Aptina camera, so normal cell phone size sensor. This is the sensor that's going to be in F3, so that's a real sensor. It's big pixels and not that many, but enough, like 4 megapixels. I mean, that 4 megapixels is like, you really don't need more if you can use your legs or optical zoom. And it has other goodies, such as it should be, well, it can do more programmability than some other sensors. It's going to have a new nice case. I hope that these are not the actual colors. But it's being used in education. This was the first course where it was used. It was done at Stanford. First assignment was autofocus, which would be like it's really cruel on a project to give students for 1 week assignment, or even for usually almost a whole quarter assignment. But in this case, the API was good enough that it gave kind of nice access to the camera. So the students were all able to implement this in 1 week. And some of them managed to actually get even better algorithm than the one that the device shipped with, which is kind of embarrassing for the engineers that ship the phone camera, but it shows the power of good tools. Here's one application, one project from the course. So this is the normal red-eye problem. If the light source was further away, you don't have that. Well, there's no room to put the flash this far away in a cell phone. You can use 2 cell phones. And if you then synchronize that with the action mechanism or FCam, you can actually, the first one, when you press the button, it sends the signal to the other one. And if synchronization is good enough, you can actually borrow its flash, and that's what they demonstrated. And even over Bluetooth, it was working. Here's another application. The idea was that you interactively make these kind of trick photos, for example. So you're sitting with your twin that doesn't exist, but this application helps you to do that, or you can hold yourself levitating, and this video shows you how you can learn to levitate. So first they have, they're doing tricks. So levitating on the desk is easier. So first the target goes there, then you indicate where are the areas that you should keep for kind of helping in the viewfinding in the next. I think the next thing is to get rid of the table. And now, okay. And then finally, okay, this is very long. Can I speed this up? Okay, so now the guy who's behind the camera is like, move a little bit, raise your hand and so forth, so that you can kind of set up the scene and take the last image, and then the combination is done as post-pros, I suppose, in Photoshop. This was a project about creating painted apertures, so getting a shallower depth of field, which in cell phone cameras, it's almost pinhole camera, so lots of things are in focus. If you want to get this shallow depth of field, you can take several images, move the camera a little bit, register to the center. And this is with 8 images. You see still quite a bit of artifacts. With 16 images, not many. With 64 images, you can't really see anything. And Mark Levoy actually made an iPhone application out of this idea. Noah Snavely used this course, and I asked him to give some feedback. I think I'm running. I'm already out of time, so well, he liked it. You should try it too. And James Davis, and it's been used in many places by now. Here are some people that were working on these various projects that I showed, and the main architects of the FCam were, well, Eddie, who's now at Google and really now is right there in the back row. This was his dissertation, and many of the images that I showed came from his work. And Andrew was the co-designer, co-chief architect of the FCam, and the first author in the SIGGRAPH paper. But that was the last team, and now I'm in a new place. I need to hire a new team. So if you know anybody who would be interested in figuring out how to solve this compute problem of the computational photography, I'm hiring, or taking interns or postdocs. This concludes my presentation. If there are any remaining questions, then we can, if we have time.
I think we have time for 2 more questions, so just a moment. No problem.
I think you showed that GPU was part of the compute ASIC.
Yeah, it's available. And why didn't we use it? Is that
How much power it has?
the problem with the current generation of mobile GPUs is that it's really, unfortunately, designed for graphics, which means that the data goes just one way from CPU to GPU to display. You can get the data back, but it's quite slow. And there's also, I suppose, the desktop you can't in that GPU, for example, render in floating point. You can only render in 8 bits. And then if you would like to have intermediate results in floating point, well, that creates trouble. We have used GPUs for simple things like warping images. But as the mobile GPUs get more powerful, then they can be used more for image processing, and that's actually what I hope to do at NVIDIA. Yeah.
Registration process, because both the things, the high dynamic range and also the out of depth focusing, registration plays a key role in all this.
Yes.
Open source, or do you have?
Could you repeat the question?
Okay. So the question was registration. Registration is a key tool for all computational photography applications, and I guess you asked whether we used open source package or whether we have open sourced it. Well, the answer to both is that no, we used our own package, and it's Nokia proprietary, and I don't have access to it now either. So, because I
can't use just as feature based because your features are not. You can just use a region based because.
We used a hierarchical method. At the really low resolution, we just used the pixels themselves to do the rough registration. And if you just take bursts without moving the camera, you don't even need to do that. For panorama application, it's more difficult. In the higher levels, we just find corner features and align those. And then repeat at next resolution and so forth.
Okay, then if there are no further questions, I think we should move on. Thank you very much, Kari.
Thank you.
So there's still a couple of free things here.